so that people can see the recording. And so I think the idea today is to do some of these examples of 2D systems, and then and I'll show you like a piece of Python code that some students put together, that's also in the Blackboard site. So I've got the Blackboard chapter 5 homework out.
Yep.
And so we're considering these sort of Romeo and Juliet systems, which is just sort of a clever way to start thinking about how to model using linear equations. So in these equations, so we have a two-dimensional system, right? And the idea here is that if R or J are positive, then if the values are positive, right, then we have love for the other. If R, J are negative, then we have dislike of the other. And then the dots, if R dot is positive, that means that the R value is increasing. So regardless of whether Romeo loves Juliet or hates Juliet, if R dot is positive, it means that Romeo is moving towards loving Juliet more. So if Romeo already loves Juliet, the feeling is getting stronger. If Romeo dislikes Juliet, the dislike is getting weaker because he's starting to love Juliet more. Same thing for Juliet, right? And so the idea is that the rate of change we're going to model as being linearly related to their feeling for the other and the other feelings for them, right? So we're going to say this is a two-dimensional system between two people, and there are two quantities that matter: how much I like you and how much you like me, or how much Romeo likes Juliet and how much Juliet likes Romeo. And each one can respond in different ways to the others or their own feelings. So in this particular example, R dot is J. So Romeo does not, his own feelings for Juliet do not come into account at all. If Juliet likes Romeo, Romeo likes her more. If Juliet dislikes Romeo, Romeo is turned off. Now, J dot here is minus R plus J. So if Juliet has positive feelings, she warms up. If she has negative feelings, she cools off. But she is inversely related to Romeo's feelings. If Romeo likes her, that's a turn off. And if Romeo dislikes her, that's a turn on. Okay, so this is how we were analyzing this. Okay, so we're going to say, that we've got R dot and J dot is some matrix times R and J. So the matrix we extract here is 0, 1, minus 1, 1. Everybody see how I got that matrix out? Right, so if I just move this J over, right, this is 0, R plus 1, J. All right, so I can extract this matrix. And we learned in the last class that it's useful to compute the trace, which is 0 plus 1 is 1, and the determinant, which is 0 times 1 minus 1 times 1, which is 1. So here we have a positive trace and a positive determinant. And we learned to compute the eigenvalues. Lambda plus minus, the formula for our eigenvalues is half of the trace plus or minus the square root of the trace squared minus 4 delta. Did I do that right? I think I did that right.
Yeah.
Okay.
I believe so.
So that's 1/2.
Oh, that's all.
Should it be?
No, that's right. Yep.
Because I got the half out.
I saw the half up front. Yep.
Yep. Plus or minus 1/2 the square root of 1 minus 4. So lambda plus minus is a half, plus or minus the I times the square root of 3 over 2. Okay, so we have complex eigenvalues with a real part that's positive. All right, so we've got complex eigenvalues and a real part that's positive. Anytime we have complex eigenvalues, this means that we're going to have a spiral. Okay, so if the eigenvalues turn out to be real, then we can have saddles and nodes. If the eigenvalues turn out to be complex, we're going to have spirals or centers. And since the real part is positive, it's going to be an outgoing spiral. So if I plot R on this axis and J on this axis, the system is going to spiral outwards kind of like that. So the right way to think about it? I think that's probably the right way to think about it. Yes. That would be the right way to think about it. And in fact, it's going to come through here vertically. And it's going to come through here vertically. All right, and the way I know that is R dot is 0R plus J. And J dot is minus R plus J. So now, if I look at R dot, if I look at the R dot equation, when J is equal to 0, R is not changing. So the place where J is 0 is the R axis. So the R axis is where J is equal to 0. That makes sense?
Yep.
So on the R axis where J is equal to 0, R dot, so on J equals 0, R dot is 0 by the equations. And J dot is minus R. So that means that right here I'm coming down and over here I'm going up. See, everywhere this thing comes around, I'm going down. So if R is a positive number, then J dot is negative. And if R is a negative number, then J dot is positive. So I'm coming through here vertically as I'm spiraling around.
So it's like an oval spiral.
Yep. And so now if I look at if I pick a point right here, right? So this point has a positive J value. And so at this point right here, the tangent vector, so these things here are the tangent vectors to the flow. See, the flow is parallel to the tangent vectors to the flow. So if I'm at a spot right there, R dot would be positive at that point because J is a positive number. And J dot at that point might be positive, might be negative. Well, we can think about what's happening along this axis as well, right? So we want to get a better picture of this. Then this axis is where R is equal to 0. So when R is equal to 0, I haven't drawn this quite as well as I could. All right, so let's think about how it crosses through here. This axis here is where R is equal to 0. Where R is equal to 0, R dot is equal to J. So I'm going to come through here, and J dot is equal to J. So I'm actually going to pass through this axis with a positive slope. I'm going to pass through here with a negative slope. Oops. Well, my spiral's all messed up now. All right, let me try to draw it better. Let me start over with the picture, right? People understand what I just tried to do?
Yeah.
So one way to think about, once you know it's a spiral, if you want to get a little bit more accurate with your spiral, you can think about how the flow is going on different lines in the graph. So what we know is that the flow is going like this along the R axis. And the further out I get, the bigger the R value is, the longer the J dot arrow is. And then along the the R equals 0 axis, this is coming through here at 45-degree lines. And the bigger up here, it's coming at a bigger 45-degree line. See, because R dot is equal to, at R equals 0, R dot is equal to J, and J dot is equal to J. So the vector is going to come through here on a 45-degree line, either one way or the other. So I'm going to come through, down, through, down, through, and then up again. That makes sense?
Yeah, I follow.
This is kind of bad over here, right? Okay. So that's how I would draw the flow for that. So what I would say here is that a quarter of the time they both like each other, but everything changes. And a quarter of the time they both hate each other. So in the first quadrant, they both like each other. In the third quadrant, they both hate each other. But the feelings are getting stronger as time goes on. See, it's an unstable spiral. So the values of the R and J are growing in their size as time goes on. Let me try to plot this one using the Jupyter Python notebook. So if I come over here and I share this tab and I come back, Chrome. Oh, what did that? Oh, well, that's unfortunate. Hit refresh. Will that work? All right. Start over. Am I no longer sharing the right screen? I might not be sharing the right screen. Let me try again.
It was showing Jupiter. I mean, I don't know.
There we go. That should be sharing the right screen now. Oh, no, not what I wanted to do. Open. Upload. So I posted this Jupyter notebook file in, both of you have used Jupyter. Daniel, you had me for
Yeah, I had you for mechanics. And
mechanics, so you've done this before. All right, so these two lines, this IPython stuff doesn't seem to work right. Okay, so now I want my equations to be 0, X is what I'm going to call Romeo, and Juliet is 1, is Y. And then for Juliet, and then the other equation, I want -1 and +1. So that's what I want my equations to be. And then you can run it, and you can see it spiraling. And see it on the vertical axis, see how they're coming through here at 45 degrees.
Yep.
And on the horizontal axis, see how they're coming through here down and vertically.
That's cool.
That makes sense?
Mhm.
So if you just come up and change your equations here, you can make this program plot whatever you want it is to plot. So the way this is working is it's defining the two equations, it's defining points in the space, and then it's making a quiver plot. A quiver are little arrows, and the arrows have length. The Vx is the X dot, the Vy is the Y dot. And so the GG is a scale, right? So we're making Vx and Vy here are make these things unit vectors. And then by making the putting this scale here, it shows you how much longer it is at different points. Actually, this might just be unit vector plotted. I think this is designed just to be unit vector plots.
Yeah, it doesn't seem like they're changing in
That they're
length,
getting
but
any larger.
the color's changing
But the colors, yeah, the color's changing.
to indicate
Oh, this
the
indicate the length. Yes.
yeah.
So you can see that they're getting longer the further out they get. They're getting stronger feelings further out. So I'll stop sharing there. I'll come back and share here again. Okay, so that was one of our examples. Let's try another one. So another one of the examples. Any questions about that first example?
Made sense here.
I'm fine with it.
So this one is referred to in the book as fire and water. In other words, whatever one of them thinks, how one of them reacts is completely opposite of how the other one reacts. So Romeo has the value A in reaction to his own feelings, and Juliet is minus A in the reaction to her feelings. So our matrix is A, B, minus A. So the trace is 0. And the determinant is A. The determinant of this system would be minus A squared plus B squared, right? I think that's right. Good. Okay. And so we've got choices for the parameters of A and B to make, right? And so the eigenvalues, okay, so our formula is trace over 2 plus or minus the square root of half, trace squared minus 4 delta. Okay, so that's going to be 0 plus or minus a half, 0 minus 4 delta.
Dr. Kling,
Yeah.
so I just looked up the determinant because I had a suspicion. So I think the minus sign should be on B, not A. Because you're multiplying the A's and then subtracting the B's.
Yeah, but if I multiply A by minus A times, so I think it's A times minus A
Yeah.
minus B times minus B.
Oh, okay.
Yeah, I
Okay.
would think first. Yeah.
Yeah, so there you go.
Okay, I'm with you. Yep.
All right. So, what do I have? So I have the half kills the 4, right? So lambda plus or minus is plus or minus the square root of A squared minus B squared. When I use the minus sign into the delta. Okay, good.
Yep.
Okay. So now,
Should it be B squared though, or
yeah, squared. A squared minus B squared, right? Okay, so if A squared minus B squared is positive, then I have 2 real lambdas. And if A squared minus B squared is negative, I have 2 pure imaginary lambda. Okay. So let's suppose for instance, that, so my system is R dot is A R plus B J, and J dot is minus B R minus A J. Okay, so now this case, the second case here, these become centers, right? So just, you know, things that look like this, right? So a center is like a simple harmonic oscillator. So what does that mean? So that means, so for this to be the case, that means that A is less than B. So A is the parameter of how I respond to me. And B is the parameter of how I respond to you. So A means how I respond to me, and B means how I respond to you. So what this model says is that if my response to you is bigger than my response to me, in other words, I'm more reactive to how you feel about me than how I feel about you, then I have this stable circular situation where sometimes we're in love, sometimes we don't like each other, but we're always kind of at the same broad level of love-hate relationship. So this second case is if your feelings to me are stronger than my reaction to my feelings, and the same with you, then we can be doing sort of the sort of stable center like relationship. So it's sort of a metastable relationship. Now, the other case, your reaction to yourself, Romeo's reaction to himself is now stronger, and Juliet's reaction to himself is now stronger than the other way around. Then we have two real eigenvalues. And we have a, and the eigenvalues are going to be positive. Well, we're going to have delta here is now negative. So I have two, so if a squared, remember delta was b squared minus a squared. And the situation I'm thinking about is a squared minus b squared is positive. So that means that b squared minus a squared is negative, which means that delta is negative, which means anytime delta is negative, it means I have a saddle. I remember that because we have this graph that has on this axis the trace and on this axis the delta, and everything over here are saddles. All delta negative are saddles. And this line where trace is equal to 0, this is the line that trace is equal to 0, those are our centers. And so our two situations that we can have basically is we can be in saddles or we can be in centers. Now, let's work it out a little bit. So let's suppose that A, for instance, let's suppose that A is 2 and B is 1. So my system is R dot is 2R plus J, and J dot is minus minus R. plus 2j. Okay, so that's my system. So my lambda was plus or minus the square root of a squared minus b squared. Let me use well, okay, so that's going to be plus or minus root 3. All right, fine. It's just
Would that be minus 2j?
minus 2j. Yep.
Okay.
Okay, so my eigenvalues are plus or minus root 3. Okay, so let's go ahead and go through the work of finding the eigenvectors. Right, so my eigenvalues are plus or minus root 3. And so my eigenvectors have to satisfy a minus lambda I times my vector is equal to 0. So I have 2 minus root 3, 1, minus 1, minus 2, minus root 3. Is that right? So I'm going to do the lambda is plus root 3 times v1 v or vx vy. Okay, I feel like I've made a mistake. Why do I feel like I've made a mistake? I feel like I've made a mistake because my system doesn't look linearly independent. Do I have my lambda value wrong? Four minus 1 is 3. Oh, stupid. No, not stupid. All right, well, let me write out the two equations. I have 2 minus root 3 times Vx plus Vy is equal to 0. And I have minus Vx minus 2 All right, so that's what I have out so far. Okay, so if I write out the two equations, I think I got that. That seem okay?
Yeah, so far that seems fine. I don't see anything before either that looks
Yeah.
weird.
So let's suppose I'm going to take the second line, and multiply everything in the second line by 2 minus root 3. So my first line is 2 minus root 3 times Vx plus Vy is equal to 0. My second line would become minus 2 minus root 3 Vx plus 2 plus root 3. Oh, perfect. Times 2 minus root 3 times Vy is equal to 0. Okay, yeah, this is actually fine. Okay, so the reason I did that is I'm going to try to solve these two equations. And so now if I add these two equations, if I add these two lines, right? So first of all, everybody understands what I've done, right? If I add these two lines, these first two things cancel.
Yep.
Now the second part would say Vy plus, now let's look at this stuff here. Well, that's 2 plus something times 2 minus something. So that's 4 minus, no, I'm not happy. 3 Vy. I was hoping to get -1 out of that. I was hoping to get -1 over because I messed up. There should be a minus sign right here. Okay. So that says Vy minus Vy is equal to 0, which says no content. Okay, so the point of doing this was to remind ourselves that the two equations are not linearly independent. Okay, so it might look at first glance like these two equations are linearly independent, but they're not, right? Because when I tried to solve the two equations for one of the unknowns, I couldn't do it. Okay, so good. In eigenvalue problems, the equations are not supposed to be linearly independent. So all you can do is you can take one of the equations. So one of the equations says 2 minus root 3 Vx plus Vy is equal to 0. So the top line says that, okay? And so what I'm going to do is I'm going to set Vy to be +1. Then Vx would be, well, let me set Vx to be +1. That might be a little bit easier. Doesn't matter which way I do it. I'm going to set Vx to be +1, and then Vy would be -2 minus root 3, which, okay, so root 3 is, what's the root 3? 1.7. So that's about -0.3. So what does that mean? What that means is for the eigenvector whose eigenvalue is plus root 3, for the plus root 3 eigenvector, there's a line that is tangent, that lies along those points. Those points are 1 unit over to the right and 1/3 of a unit down. And so this line here, oh, a really shitty line, that goes through this point and that point. No, it goes through that point and that point. So that line there's a line. So this is the line that corresponds to that eigenvalue. And that axis is unstable because the eigenvalue is positive. So that's the axis on which things are going out. So what I've done is I found the two eigenvalues. I took one of the eigenvalues. I wrote down the eigenvector equation. I figured out the two equations were not linearly independent, which was a consistency check that I hadn't messed up yet. Then I took one of the eigenvector equations, and I figured out the line that goes along with that. So this line, because that's the positive eigenvalue, is the unstable direction. That is the unstable manifold. Okay, so now I'm going to go back and I'm going to do the lambda is minus root 3 eigenvalue. So now I have 2, 1, -1, -2, minus root 3, 0, 0, minus root 3, all that times Vx, Vy is equal to 0. So this is A minus lambda I times V is equal to 0. It's my eigenvector equation. So I have here 2 minus root 3, or 2 plus root 3, because I have this minus sign and the minus sign's in the eigenvalue, times Vx plus Vy is equal to 0. Okay, so if I stick in Vx equals 1, then Vy would be minus 3.7, right? Because root 3 is about 1.7, so 2 plus root 3 is about 3.7. Okay, so now if I come up here, Vx is 1, makes me unhappy. Makes me unhappy? 2. Okay, I guess that's all right. So if I go over 1, I got to go down like 4. So that's like here and here. So there's another axis that's coming through here like that. And that axis is the stable axis. So what that means for the flows, so if I've done this correctly, all right, that was the stable axis because the eigenvalue was negative. The eigenvalue is negative, then the axis associated with the eigenvector is the stable manifold. So I've got a shallow running unstable manifold here. And then according to my math, I had a very steep stable manifold there. And so what that means for the flow is going to be this way or that way. It's going to have to asymptote to this line, right? So it asymptotes out to this black line. So it's going to come from close to here, but peel off. And then in here, it comes in and then bounces out. Or it comes in and then bounces out like that. So that's my flow. So how do I interpret this in terms of Romeo and Juliet? Okay. So let's ask questions, right? Will the end state be good for both? In other words, no matter where you start, where do you end up? No matter where you start, you either end up out here or you end up out there.
You just end up away.
Yeah, but you end up away in either the fourth quadrant or the second quadrant. So if you start anywhere this way of the red line, if you start anywhere to the right of the red line, then the end state of the stable axis is Romeo loves a Juliet that dislikes him. And that Romeo's love for Juliet is a little bit stronger than Juliet's love for dislike for Romeo. See, if I end up down here in this black dot somewhere around this black dot vicinity, my R value is positive, my J value is negative. So anywhere to the right of that red line, I'm either going to swoop down in that first quadrant, but end up in the fourth. I'm going to hairpin out of the little inside triangle, but I'm going to end up with Romeo loving Juliet and Juliet disliking Romeo. On the other hand, if I'm on the other way, so to the left / bottom, I end up with Juliet loving Romeo, who dislikes her. And it just depends on what the initial condition is, right? So this red line is dividing the initial conditions. You can think of it as you show up at the love booth asking for advice. If you fill out how much you love the other and how much they love you, and at the moment that you show up at the love booth, you're here, even if you both love each other today, so that black dot, they both love each other today, but they're going to end up with Romeo loving Juliet and Juliet disliking Romeo. If they start off here, where Romeo loves Juliet, but Juliet dislikes Romeo a lot, counterintuitively, they will end up with Juliet loving Romeo, but Romeo not liking her. If this is the model.
It's a tough model.
That's a tough model. You should hope not to be in a relationship like this one.
And then there's the unstable fixed point.
Yeah, now,
where
if they
no one
start
cares
off
about
on
anyone.
this line, they will end up in apathy. So the only other condition is if they start off on that red line, anywhere on that red line, they end up fizzling out to total apathy on both sides.
Yep.
This is a really tough model then, huh?
This is a really tough model. So they will not end up happy, right? Together. They will not be happy together in the long run. Okay, so we could do other examples, but why don't we just make sure we got this one right? I'm going to stop broadcasting there. I'm going to come back here and share the screen. Oh, did it log me out again? No, wait, what did I do? Ah, connection keeps failing. Okay, stop sharing. Close, close, close. Okay, log back in. I just want to double check that we got it right? So we'll put in those numbers and see that we got it right. Jupiter's a little cranky today. Wow, I should have just opened it up on my own computer. I don't know why I didn't do that. That would have been the smart thing to do. Okay, now I can share that screen. Okay, so we should be looking at this. And like I said, I think these lines it doesn't like. So we're on that. Okay, and our model was 2x plus r minus r minus 2y. Yeah, so if you look here, everything up here is coming down here. There's a line that's running right through kind of here. There's a shallow line running through here. We should probably add the line that we found, right? But there's a shallow line. See how these top arrows are coming in And there's a
Yep.
shallow line right through here, kind of, where you can see that this is what's happened. See how down here, if you start down here a little bit this way, you turn off that way, but a little bit this way, you turn quickly that way. So I think we did it right. Yeah, I'll just go with that, but you guys can like double check. All right, so that's more or less what we're doing with these types of problems. You can plot them, you can figure out what they are. You know, it's fun. I had a class that made a poster. You know how we have the spring research festival thing? They actually showed up with this love poster, and they had little tickets that you could fill in, and they would tell you what would happen to your relationship.
Oh no.
They were the love doctors. And they had like, you know, you would say how much you were in love and what your relationship was like, and then they would quickly compute for you what would happen to your relationship.
Which models were they using? This one or?
Well, it was whatever the possibilities were. They worked through all the possibilities for all the different values of the models, and whatever you
Oh,
showed
okay.
up with, then they would give you the